Hello everyone, Ryan Jackson here. Hope you're having a great day. We're going to talk about NFPA 70E once again. I know most of my videos are on the National Electrical Code, but NFPA 70E is a very important document. It covers electrical safety in the workplace. So what are the requirements for making sure you come home with the same number of fingers and toes that you went to work with, right? That's the whole idea. So 70E has been around since 1975. And this newest edition is the 2004 edition, and there actually weren't that many changes. In fact, one of the cool things about NFPA 70E is on the first couple of pages, and I know you can't read this in the picture, but on the first 2 pages before you get to the table of contents, it actually gives you a little bit of a history of some of the revisions that were made in the different editions. And one of the things you'll notice if you have a copy of the book is as you're reading through, it'll tell you what happened in 2005 and 2008 and 2011. So you've got all this material here, and you've got a paragraph about each of the revision cycles until the very last one. And it actually says, revisions to the 2024 edition were for clarification, usability, and to comply with the NEC style manual. That's it. So is that all that changed? No, of course not. There were some technical changes, but for the most part, there really weren't that many, earth-shattering, change the way you work on stuff types of changes. And maybe that's a good thing, Maybe we're close enough to having it perfect, right? It'll never be perfect, but maybe we're close enough that we're not having to do wholesale changes like we've had to do for the last several editions. So a lot of changes just for usability and to comply with the NEC style manual. So not a whole lot to talk about. Every article now has a scope. So you go to Article 110, 110.1 is going to have a scope for what Article 110 covers. Article 120, Section 120.1 is going to be the scope for what Article 120 covers. So every article has a scope, and quite frankly, that probably should have been the case all along. Another change that was made kind of standard wide was the use of the word shock. So when it comes to electric shock, we call it electric shock because that's what it is. That electric shock, when we as electricians talk about shock, we're probably talking about electric shock. But if you talk to somebody that's not in the electrical industry and you say the word shock, maybe they're thinking about electric shock. Maybe they're talking about a shock wave. Maybe they're talking about, something that's surprising and shocking, So when we say the word shock in NFPA 70E, we need to be specific. Are we talking about electric shock? Or are we maybe talking about a shock wave that could be created from an arc blast? So where it used to just say shock, now it will say electric shock where it's appropriate. So you'll see a lot of gray highlights as you go through the standard. And of course, changes are covered in gray highlights, so they kind of jump off the page for you, and you'll notice the word electric shock all throughout the standard is now used where just shock was used before. Another thing that we had, and I'll go ahead and move over to the presentation here, Article 100. Just like we had in the 2023 version of the National Electrical Code, all definitions are now located in Article 100. For a small standard like this, probably a good thing. They should all be in the front of the standard, in my opinion. Again, just like the 2023 NEC, article-specific definitions now have an article number in parentheses, and I'll show you an example here in just a minute. And of course, several definitions were added, deleted, or revised. All right, so when we read the scope of Article 100, it says Article 100 only contains definitions that are essential for properly applying this standard. It does not include commonly defined terms or common technical terms defined in other codes or standards. All right, so if you're looking in NFPA 70E for the definition of glove, you're not going to find it because when we say the word glove in 70E, we just mean glove, right? The same definition applies in 70E as it does in Webster's dictionary. So we're not going to add a definition in Article 100 for a commonly understood term. Everybody knows what a glove is. What's a protector? Well, a protector, if you were to go to Webster's, I'm sure has a lot of different definitions. There's different types of protectors. In NFPA 70E, when we say the phrase protector, we're talking about the thing that goes over your glove. So protector does have a definition in 70E, but glove does not. All right, so talking about the change. If a definition, and this is in the article scope, if a definition includes an article number in parentheses, then that means the definition only applies to that article. So here in the example, we've got the definition for automatic, and you can see at the end of the definition, there are no numbers, there's no parentheses, there's no brackets. So that means that this phrase is used throughout the standard, it applies throughout the standard, and there's nothing special about it. The next definition, accessible as applied to equipment, you can see has the number 70 in brackets, and then it says 100. Well, what bracketed references in Article 100 means, and that's true in 70E, it's also true in the NEC. Either way, in NFPA standards, if you have a bracketed number, that means that the text you just read came from a different NFPA standard. So where did the definition for accessible come from? Well, it came from NFPA 70. And that's what the 70 is. It then says 100. That's what article in NFPA 70 this came from. So NFPA 70, of course, is the NEC. So the definition of accessible comes from NFPA 70, the National Electrical Code, and it's found in Article 100. The next definition talks about battery effect. And let's take a look at a couple of things. Here I've got the letter N next to the battery effect. That means that this is new material. Now, you're going to find this throughout 70E, not just in the definitions, but everywhere where there's new material. You're going to see that little letter N in a circle. It also has an article reference at the back of it. It says 310 in parentheses, which means that definition only applies to Article 310. So if you're not thinking about Article 310, there's no reason to read this definition. All right, so that's kind of the way Article 100 works. As far as actual changes in Article 100, we did add a new definition, and that's for protector, which is a mitten or a glove that's worn over your rubber insulating gloves. All right, so certainly not a new concept here. We've had protectors for a very long time, but we used to call them what? We used to call them leather protectors. And we didn't have a definition. We just kind of assumed that everybody knows what a leather protector is. And we shouldn't have made that assumption. I think everybody knows what a glove is, but not everybody knows what a leather protector means. So what's a leather protector? Well, it is the mitten or glove that goes over your rubber insulating glove. All right, so this is your shock protection, right? Your rubber insulating glove. This is the piece of PPE that has a voltage rating, or it's going to have a class 0, 00, what have you. So this is your shock protection. Now, a protector goes over your shock protection, and really it does two things. It protects, but it protects against what? Well, it protects the rubber glove from getting cut up and getting holes poked in it, right? Because if you put a hole in this, then you might as well be wearing bare skin. So it protects the glove, but it also protects you. This is your arc flash protection for your hand. So it can be leather like this, or it can be a different material. So we no longer talk about leather protectors, we just talk about protectors. And we added a definition for them in Article 100. All right, let's move into Article 110, which is General Requirements for Electrical Safety-Related Work Practices. Let's start with 110.2, Electrically Safe Work Condition. Super important section in NFPA 70E. 110.2 is one of the most important sections in the entire book. We added an informational note about documenting the electrically safe work policy. Verifying proper fault current ratings is now part of determining whether or not a normal operating condition exists. Super important section there. An informational note was added for evaluating water-damaged equipment, and an exception was added to recognize the need for operating a disconnect while it's energized. That one's almost like an eye-rolling change, but technically it probably does need to be there. So let's jump into 110.2. 110.2a, policy. Employers must create, document, and implement an electrically safe work condition policy. All right, so you have to have an electrical safety program, right? That's the overall big picture that you have for your company. Whether you're a contractor or you're a facility, you need to have an electrical safety program. Part of that program needs to include an electrically safe work condition policy, and that policy needs to include when you need to establish an electrical safe work policy, or excuse me, when you need to establish an electrically safe work condition. It'll talk about doing hazard analysis, whether we're talking about shock analysis, electric shock analysis, or arc flash risk assessments. So we need to create an electrically safe work condition policy, tell us how to create an electrically safe work condition, and when one is required. When implementing safety-related work practices, the first policy must be to eliminate the hazard. All right, so we have what's called the hierarchy of risk control. And if you're familiar with NFPA 70E, you're probably already familiar with the hierarchy of risk control. That is where we say the first way to establish safety is to eliminate the hazard. If we can't eliminate the hazard, then there's other things that we can do in a particular order. And we're going to talk about that here in just 1 second. The electrically safe work condition policy must comply with 110.2b, and that's what we're going to read next. So A simply says, listen, you need to create a policy. And what needs to be contained in that policy, we're going to talk about in 110.2b. There's an informational note here that says Annex F has examples of hazard elimination. Elimination is always the highest priority in the hierarchy of risk control covered in 110.5H3 because it's the most effective. So if I want to not get injured, then obviously the best thing I could do is to eliminate the hazard. Or if I can't eliminate the hazard, maybe I can substitute to a lower hazard, right? A lesser hazard. Maybe I've got to troubleshoot a motor. You know, one of the things that people have a misconception of is whether or not you can work energized. Well, sometimes working energized is part of being an electrician. Now be careful here. There's two different types of energized work. There's troubleshooting, diagnostics, right? That has to be done energized a lot of times. I can't measure for voltage if it's not on, right? I can't troubleshoot why something is behaving in a certain way if it's not on. We're okay with diagnostics and troubleshooting. What we are not okay with is repair work, where you're actually going in there and you're, tightening screws and using wrenches and everything else inside of energized equipment. We don't want people repairing equipment. That can almost always be done while it's off. Troubleshooting? Hey, if you can turn it off, turn it off. But if you can't eliminate the problem? Well, substitute to a lesser hazard. Maybe I'm troubleshooting a motor circuit. Can I troubleshoot the low voltage control circuit instead of the power circuit? Might be a good example of substituting to a lesser hazard. Is there a hazard in troubleshooting the control circuit? Sure. Is it the same hazard as troubleshooting the line voltage to the motor? No, it's not. Engineering controls, awareness, administrative controls, and then the last one is wearing PPE. Wearing PPE is the least effective way of removing risk, right, and removing hazard. So PPE is always the last resort. The first thing we want to do is to eliminate the hazard. There's another informational note here that says the electrical safe work condition policy could be documented in the employer's electrical safety program or similar. And I think that's usually where you would have it. Like I said before, you need to have an electrical safety program. That's the big picture, right? Within that program, you probably need to create the policy that we just discussed and put it in the program. I don't know where else you would document it if it wasn't in the electrical safety program. 110.2b. When required. When do you have to have an electrically safe work condition? Really, really important section here. They rewrote this section, kind of reorganized it from a technical perspective. not much really changed here. What we used to have as positive text, we now kind of created into an exception, and they rewrote it, added some information. So conductors and parts operating at 50 volts or more must be put into an electrically safe work condition before an employee performs work if the employee is within the limited approach boundary. All right. So we haven't talked about what the limited approach boundary is yet, but the limited approach boundary is a shock protection boundary. It has nothing to do with arc flash, has everything to do with electric shock. So here in the photograph, if this is energized and if this is 480 volts, the limited approach boundary is 3'6". And if we go back, it says what? Conductors and parts above 50 volts have to be put into an electrically safe work condition. Now that means that it's shut off and it's tagged out and it's measured to verify the absence of voltage and some of the other steps, right? So it's not just a matter of shutting it off. It's going through the whole process. We have to have an electrically safe work condition if the employee is within the limited approach boundary. Now, with the cover on, there is no limited approach boundary, right? It's with the cover off. So if I have exposed live parts and I'm within 3.5 feet of them, that equipment needs to be in an electrically safe work condition unless we meet the exception that we're going to talk about. Or item 2, I have to have an electrically safe work condition if the employee interacts with equipment where conductors or circuit parts are not necessarily exposed, but an increased likelihood of injury from exposure to an arc flash hazard exists. Okay, if the circuit conductors or circuit parts are not exposed, then there's not a shock hazard, right? An electric shock hazard. But could there still be an arc flash hazard? Absolutely. What we're showing here in the picture is a rack-in style circuit breaker. And that absolutely is a piece of equipment or procedure that has an increased likelihood of injury. When I'm racking that circuit breaker in, if it's an energized piece of equipment, just the process of racking that thing in and making contact could potentially create an arc flash. So that thing needs to be shut off before I start racking breakers in or out. All right, so that's item 2. What used to be a list within the positive text of the language is now an exception. It says exception number 1. Normal operation of equipment is allowed if a normal operating condition exists. And a normal operating condition exists when the following conditions are met. All right, there's a massive misconception here, and I kind of already talked about it, where people roll their eyes and they say, oh my God, NFPA 70E, holy cow. You got to dress up like an astronaut to turn on a light switch. No, you don't. Well, but you do to plug a thing in. No, you don't. Stop pretending you know what the standard says if you've never read the standard. It doesn't say that. It says normal operation of equipment is allowed if a normal operating condition exists. Can I walk up to those disconnects here in the picture and use the disconnects? Yeah, that's normal operation of equipment, right? That's what it's for, is to disconnect it as long as a normal operating condition exists. Now look, if this thing is rusted out and there's exposed parts and it looks like it's ready to blow up, that's not a normal operating condition. So no, you couldn't just go up to it and work the handle. You'd have to shut it off and dress up, right? But normal operation of equipment is allowed if a normal operating condition exists. Now, what is a normal operating condition? That means the equipment is properly installed. All right, so looking at this photograph here without knowing anything else, it appears that equipment is properly installed. All right, so it has to be properly installed, has to be properly maintained. When this equipment was installed, perhaps it was properly installed, but it's not been properly maintained. So can I go up to this thing and start flipping circuit breakers on? Absolutely not. We have no idea if there's loose metal parts in there, right? If the inside has rust and it's got parts that are ready to fall down. No, there is no normal operation of this equipment because this is not in a normal operating condition. If I needed to work on that panel board, I would need to what? I would need to shut it off. I would need to establish an electrically safe work condition. Item 3. The equipment needs to be rated for the available fault current. Now, that's added here in the 2024 code. Is it new? Not necessarily. I mean, one of the things that the standard has always said is that the equipment has to be properly installed and installed in accordance with the instructions, which would include that it's rated for the available fault current. But this is an important enough concept that we want to add it here so that it stands alone. Look, the equipment needs to be rated for the available fault current. So where I have this circled, you can see this thing is rated for what? 200,000 amps of available fault current. That's a ton. That is an absolute ton of available fault current. But if I keep on reading it, it's only good for 22,000 if it's equipped with main lugs or feed-through lugs and no overcurrent device installed upstream of it. Okay, so if this was the service disconnect, for example, it does not have a 200,000 amp interrupting or short circuit current rating. It only has a 22,000 amp short circuit current rating. If this was coming straight out of a transformer and it went main lug, which normally we can't do that. There are instances where you can if you look in the NEC, but usually you cannot do that. If you were able to, though, the available fault current or the short circuit current rating, not 200,000, it's only 22,000. So make sure everything is rated for the available fault current. This is easier in a modern installation than it was in older installations because now under the 2023 national or under the 2020 National Electrical Code, 408.6 says you need to mark the available fault current at every panel board. So determining the available fault current is a lot easier today than it was in yesteryear. So make sure the equipment is rated for the fault current. Number 4, equipment is used in accordance with the listing and manufacturer's instructions. Obviously important. Equipment doors need to be closed and secured. So again, we're talking about normal operation of equipment. Can I walk up to this switchboard and turn these breakers on and off? Yes, that would be normal operation of equipment. And it appears that this equipment is properly installed, properly maintained, suitable for the fault current, used in accordance with its listings. Equipment doors are closed and secured. Covers are in place and secured. All right, so over here on the left, that panel board has a lot of circuit breaker fillers, right, blanks, but at least they're there. The one on the right, yeah, is there normal operation of that equipment? Absolutely not, right? We don't know what kind of critters and objects and things have gotten inside of that panel. So I can't just walk up to it and turn on and off the breaker because that is not a normal operating condition because the covers are not in place and secured. Item 7, there needs to be no evidence of impending failure. All right, so here we have this panel board on the outside of a dwelling unit. And you can see that the snow has completely destroyed it, right? This massive snowstorm, 3 feet of snow, took the mast right off the roof, racked the breaker out of square, or racked the equipment out of square, and now it looks like this. Is that evidence of impending failure? Absolutely. Can you walk up to that thing and start turning off breakers? No, absolutely not. Where are the screws that once held that equipment to the wall? They've either withdrawn or they've sheared off. Either way, we've got at least the heads of the screws, if not the entire screw itself, bouncing around inside that equipment. If I walk up to it and just open the door, that could jostle it enough to create an arc flash. So no, this is not a normal operating condition. Therefore, there is no normal operation of it. So I would have to do what? I would have to establish an electrically safe work condition. In this instance, I would need to call the utility and have them come out and disconnect the power upstream before we started playing around with it. There's another informational note here that we added for the 2024 that tells us to take a peek at NEMA GD1-2019, evaluating water-damaged electrical equipment for information about equipment that has been exposed to water. All right. This is a free download from NEMA. If you go to NEMA.org, you'll need to create a username and password, but it's free. And I recommend doing it. NEMA has a lot of good resources out there that are free. So go to NEMA.org, get yourself this document, Evaluating Water-Damaged Electrical Equipment, for evaluating equipment that's been exposed to water. Is this a code violation right here? Well, installing indoor rated equipment outdoors is obviously not allowed. However, if you're doing this during the course of construction, right? If you're installing this equipment that's for the permanent installation and you're doing it while the building is under construction, that is okay, as long as you protect it from the weather. And that's something found in, I think, 110.12b, or maybe it's 110.13 in the National Electrical Code. So is this okay? Yes, if it's protected. If it's not protected, well, then we got a problem. Now, if you're in the workplace, it's not so easy to just put on your inspector hat and say, hey, that's a code violation, rip it out. You know, sometimes if we're in the real world, we have to evaluate just how dangerous or how damaged a piece of equipment is. And NEMA has standards that can help you with that. Exception 2, and this is new. Operating an energized disconnecting means or isolating device while establishing an electrically safe work condition is allowed if a risk assessment shows that there's no unacceptable risk. All right, well, part of establishing an electrically safe work condition is shutting off the power. So how can I shut off the power? That's working on equipment, and it's not in an electrically safe work condition because you're placing it in. Okay, hang on. You have to be able to shut off disconnects while you're creating an electrically safe work condition. So, yes, can you shut off the disconnect? I mean, first of all, let's look at that disconnect. That appears to be in normal operating condition, which means I can have normal operation of it. I can go up there and I can shut that thing off. What if it was not in a normal operating condition, but there's no disconnect upstream? Well, maybe it's the service disconnect. Well, if we do a risk assessment and we see that there's no unacceptable risk, then that might be something that we can do. We still have exception 3. Energized work is allowed if the employer demonstrates that the task is not feasible while de-energized due to operational or design limitations. I like to use solar PV as an example for this because it's pretty difficult to shut off solar, right? Unless you're shutting off the sun, you usually can't really shut off solar. You can shade the module, but that's not always feasible, depending on what we're doing. So this could be an example of where shutting it off just isn't feasible due to operational or design limitations. Exception 4, energized work is allowed if the employer can demonstrate that shutting it off introduces additional hazards or increased risk. All right, so here in this photograph, we've got a hazardous location, right? We've got all of these barrels of gasoline. You do not want to work energized in this location. Any sort of arc or spark would blow up the room and we'd all be dead. So working on this thing energized in that location would never be allowed. But maybe shutting off the ventilation system would create additional hazards, right? So which is a greater hazard? Me getting shocked by working on the ventilation system, or me shutting off the ventilation system and creating an accumulation of ignitable vapors that could then blow up? It's something that the employer is going to have to weigh out and figure out, okay, which is a greater hazard? And if the hazard of shutting it off is greater than you working on it energized, well, then you can work on it energized if you go through the hierarchy of risk, right? See if you can substitute it to a lower risk, see if you can use engineer controls, awareness, all of those things, right? And then down to PPE. Exception number 5. Energized electrical conductors and circuit parts operating at less than 50 volts need not be energized if there's no increased exposure to electrical burns or arcs. All right, so 50 volts is where we start getting concerned from a shock perspective. If it's lower than 50 volts, you can't get enough current to create a fatal condition. Now, I'm not putting forth a challenge, right? Oh, I went in a swimming pool and put a transformer in my mouth and I got... I'm saying, look, in the real world, in a normal condition, 50 volts is not going to kill you. Okay, it's not a high enough voltage to drive the amount of current needed to stop the human heart or even create a dangerous electrical shock. So, from a shock perspective, 50 volts is where we start to get concerned. But that's not the only hazard. We could potentially have arc flash, possibilities at lower than 50 volts. Probably not realistically, because you do need to have enough voltage to sustain an arc, but we could have thermal burns, things like that. So electric shock is not the only hazard. So energized parts do not need to be shut off if it's less than 50 volts and there's no increased exposure to electrical burns or arcs. 110.2c, requirements until the electrically safe work condition is established. Conductors and equipment are not in an electrically safe work condition until Article 120 has been followed. All right. So Article 110, the section we're reading, tells you when you need an electrically safe work condition. Article 120 tells you how to create one. All right. And until you've gone through the entire process, you are not in an electrically safe work condition. So one of the things that we have to do is we have to figure out all sources of electric supply. Once we've figured out what we need to shut off and we go ahead and shut it off, does that mean that we're in an electrically safe work condition? No, absolutely not. We need to lock it out or put a tag out device on it. We need to put our tag on it. We need to verify the absence of voltage. Only after you've gone through the whole thing are you in an electrically safe work condition. So until you've done it, it's considered on. So when I'm measuring for the absence of voltage, right, I've shut it off, I've locked it out, I've got in there with my tester. Even if it shows that it's off, until you verified it, we got to pretend that it's still on. All right, so until you're done with Article 120, you're not in an electrically safe work condition, which means appropriate safe work practices must be followed until the conductors and equipment are in an electrically safe work condition. All right, so that takes care of Article 110. Let's go ahead and jump into Article 120, which is establishing an electrically safe work condition. All right, 120.5, lockout tagout procedures. Informational note was added to remind workers of the possibility of energized neutral conductors. Not something that comes up too terribly often, but it can. So 120.5, lockout tagout procedures. The employer must maintain a copy of the procedures required in 120.5 and make them available to all employees. All right, this example that I'm showing here in the photograph, this was at a hospital that I was fortunate enough to go on a tour of, and they had the lockout tagout procedures for each individual equipment printed and attached to all the different equipment. Awesome. I mean, outstanding job. Unfortunately, that's probably not how most places are. I wish that was the case. But for this, it actually told us exactly what needs to be shut off, how we can verify it, where to put the lock, where to check the voltage, right? They printed it out and put it on each individual equipment. If you work at a facility and you're able to do that, do it, right? Make everybody's life better and safer. If you don't work at a facility and you're a construction electrician, this might not be quite as easy. But here's the deal. If you're an employer, whether you're a contractor or a facility, you've got to maintain a copy of the procedures required in 120.5 and make them available to all employees. So you need to create a lockout tagout procedure. You need to train your employees on it, and you need to give them that policy. Locating the source, 120.5A1. Up-to-date single-line diagrams must be referenced. If they're not available, the employer must determine an equivalent way of finding all sources of electrical energy. This is step one in creating an electrically safe work condition, is identifying all sources of electrical energy. And quite frankly, this is usually the most difficult part. Knowing what to shut off is the hard part. So if you have up-to-date single line diagrams, you got to use them. And again, if you're at a facility, hopefully you have access to up-to-date single line diagrams. If you're a construction electrician, maybe you have them, maybe you don't. If you don't, then the employer needs to determine an equivalent way of finding all sources of energy. What changed here in the 2024 edition is they added an informational note. It says, look, determining the sources of supply may include scenarios where the neutral remains energized after the ungrounded conductors are shut off. All right, so here in the picture, I'm showing a panel board, and although it's difficult to see, they're sharing neutrals in this panel board. So we're using multi-wire branch circuits. If it's installed after the 2008 code was adopted, then the disconnecting means, the circuit breakers, should have a 2-pole or a 3-pole breaker, or at least a handle tie to tie all of the shared phases together. All right, so that's been in the NEC since 2008, but I got news for you. Not every building was built before 2008. I was an electrician long before 2008, and I did commercial work, and I can tell you that every time I could share a neutral, I did share a neutral. And yeah, if it was new construction in a perfect world, then I would put the 3 phases next to each other, circuits, 1, 3, and 5, or 6, 8, and 10, or whatever. But boy, I'll tell you right now, if I was in an existing panel board where you've got openings, scattered throughout, sometimes circuits 1, 41, and 16 might share a neutral. And if you're working on a piece of equipment and you're working on circuit 1, you shut off circuit 1, well, that doesn't mean you shut off circuit 41 and 16. So the neutral conductor for those 3 could still be energized. So the informational note, it doesn't really tell you what to do or how to do it. It just says, listen, determining the sources of voltage might include considering scenarios where the neutral remains energized after the ungrounded conductors are shut off. So just something to kind of keep in mind. All right, 120.6, the process for establishing and verifying an electrically safe work condition. Verifying the absence of voltage at the point of work is now emphasized. I think this is a really good change. This is something that's quite important. 120.6, the following steps must be taken in this order to establish and verify an electrically safe work condition. Now, as we've said before, the first step, determine all possible sources of power and check appropriate drawings, diagrams, tags, and similar. So we need to figure out exactly what needs to be shut off. So here at this facility, they've actually printed instructions telling you what needs to be shut off, because if it's just a matter of shutting off one breaker or one disconnect, that might be simple. What if it's got a UPS system? What if it has a battery backup? What if it has a generator, right? What if it's one piece of equipment that's supplied by 2 different circuits? So item 1, as I mentioned before, this can often be the most difficult part. Item 2, interrupt the load, then open the disconnecting means for the equipment. All right, so once I've figured out what circuit supplies this air conditioner, because maybe I need to work on the supply side of this air conditioner, maybe shutting off the breaker, or working on the supply side of the disconnect, changing fuses. I might have to shut off the breaker. What if I'm working on the unit? Well, shutting off the disconnect might be all that I need to do. But which would be better? Shutting off the disconnect while the motor's spinning, or shutting off the motor by turning off the thermostat and then opening the disconnect? Yeah, probably a better thing to do would be to interrupt the load, then open the disconnect, right? So shut the motor off at the thermostat. That's not locking it out. That's not isolating it, right? That's just stopping the motor spinning. Then work the disconnect. Then item 3, if possible, and this needs to be changed badly in the standard, it should not say if possible. It should say if it's not going to create additional hazards, visually verify that the disconnecting means is open by viewing the blades of the switch. Here in this photograph, you can actually see the blades move when you work the disconnect. If we can see the blades move, well then yeah, let's watch the blades move. Why not? That's increased safety. Could I open the cover of that disconnect? and watch the blades move? Sure, I guess, but we don't want you doing that. God, don't put yourself in harm's way in the name of safety, right? So yeah, if it's not going to increase your risk, go ahead and watch the blades move. Or if you're using a circuit breaker like this, withdraw any draw out type circuit breaker to the test or disconnected position. So you push the button, right, and you can see the draw out position. It says that it's open or it's under test position so that we know it's open. Item 4, release any stored electrical energy. A lot of times this is having to do with capacitors, and a lot of times with capacitors now, because more and more equipment has capacitors in it, a lot of times if there's a bleed off resistor, a lot of times the way you release any stored energy is to just wait. You shut it off and you just kind of look at your watch and you wait. I saw it was a small residential solar PV inverter where the instructions say, do not open it until after shutting off and waiting 30 seconds. And it's like, how stupid is that? You shut it off and hang out, wait for 30 seconds? Not stupid at all. Not stupid at all, because there's still power in those capacitors. And those capacitors take a little bit of time to discharge, all right? So let's release any stored electrical energy. Number 5. Block or relieve any stored non-electrical energy in devices to prevent energizing electrical conductors or equipment. So usually what comes to most people's mind here is the springs on a circuit breaker like this, right? On a circuit breaker where you have to, prime the handle. What are you doing? You're putting tension on the spring. So when that spring is under tension, we need to relieve that tension so that it doesn't automatically de-energize, or automatically energize, pardon me. Item 6, apply lockout tagout devices in accordance with established and documented procedures. All right, so figure out what to shut off, shut it off, relieve any electrical energy, relieve any non-electrical energy, put your lock on it or your tagout device in accordance with established documented procedures. So that's where the last section that we read, the employer needs to create a lockout tagout policy. It's going to tell the employees what to do and how to do it. And then this is saying that we need to actually do it. We need to follow those procedures. We're going to put our lock on it. We're going to tag it out, do all of those things. Item 7, verify the absence of voltage by testing at each point of work for both line to line and line to neutral or ground voltage with a properly rated tester. All right, so we need to make sure we're doing this at the point of work, at each point of work. If you have a large piece of equipment, this becomes even more critical. If you've got a large piece of switch gear, for example, multi-section switch gear, we need to make sure that every section that I'm actually working on is going to be de-energized. Don't just check one piece of the equipment, right, that's massive. Make sure you're checking it actually where you're going to be doing the work. Test it line to line and line to neutral or line to ground, which of course is why you can't use a proximity tester like this. If you're using a little hot stick like this, a proximity tester, those have their uses, but creating and verifying an electrically safe work condition is not one of their uses, okay? Those just give you a little bit of information. When we're actually testing to verify the absence of voltage, we need to test it line to line and line to neutral with a properly rated test, and we need to verify the functionality of the tester on a known voltage source before and after each test. All right, so a live, dead, live, right? We're gonna check the meter on something we know is on so we can check that the meter works. Then we're going to check and make sure that what we think is off is indeed off. Then we're going to go back and we're going to check that the meter still works, right? Maybe we want to make sure we didn't hit the hold button, while the meter was on 0, right? You hit the hold button and you test it. If it was actually on and it reads 0, well, then when you go back to test your meter on a known voltage source, if it still reads 0 and you know that what you're testing is on, well, then we know something went wrong, right? So a live, dead, live test. Make sure you're testing your tester, test the circuit you're working on, test the tester again. Item 8 talks about grounding circuit parts when needed. Not often that comes up, but when it's necessary, we do need to do it as well. So there's 8 parts to creating and verifying an electrically safe work condition. All right, Article 130, work involving electrical hazards. 130.4, the electric shock risk assessment. The shock tables were revised very slightly due to rounding errors between metric and imperial systems of measurement, and the table note was added about higher elevations. Okay, this is kind of a frustrating one, but we had to change some of the electric shock protection boundaries. For example, if we open this thing up here, if we're looking at phase-to-phase voltage, limited approach for movable conductors, so maybe like an overhead line, right? Something that moves around. In previous versions, it said 3 meters or 10 feet. Okay, well, 3 meters is not 10 feet. A meter is, I think, 39.3 inches, somewhere in that neighborhood. So very seldom are you going to have 3 meters and 10 feet. Yeah, horseshoes, hand grenades type of thing, that's fine. But here's the problem. It didn't comply with OSHA. When we made these little round these roundings in the NFPA 70E, we're like, 3 feet, 3 meters, 10 feet, close enough. Well, OSHA says 3 meters. So when we say 10 feet, that's not 3 meters. So when we rounded them, we didn't round them conservatively. We rounded them in the way of not establishing safety. So I know this is dumb. I know it, but it is what it is, okay? The fact is, previous versions of this table did not satisfy OSHA. All right, so the shock protection boundaries changed, and often it changed by 1 inch, right? I mean, seriously, look over here. In the 2021 code, it's standard, we had 751 through 15,000 volts, and now we changed it 5,000, 15,000. But look over here all the way to the right, where it used to be 2'2". Now it's 2'1", and it's like, oh, seriously? You changed it for 1 inch. It didn't comply with OSHA before, okay? So, yeah, you can roll your eyes and say how dumb this is, and I get it. But the fact of the matter is, this standard, it needs to at least satisfy OSHA, right? I think we all agree with that. So we had to change the table. They also added a note here to the table, and this actually correlates with OSHA requirements. That says restricted approach boundaries. Now, that's not having to do with arc flash, right? That's shock. So restricted approach boundaries are based on an elevation of 3,000 feet or 900 meters. And right off the bat, you have to wonder, like, why isn't it more specific? Because 900 meters probably isn't exactly 3,000 feet. For higher elevations, adjustments must be considered. Okay. At my house, I live at 5,000 feet above sea level. And when I travel and I go to sea level and then I come home, I can tell a difference in the air, right? The air is a lot thinner at my house than it is in Florida. What does that do to the dielectric strength of air? It's not the same, right? The dielectric strength of air at 5,000 feet is not the same dielectric strength of air at sea level. So OSHA has this table here, and it says, look, you're going to take the approaches that we just talked about, the restricted approach, and you're going to multiply it by these correction factors based on your altitude. Okay, so this table here is actually not in NFPA 70E because the standard just says, hey, you might need to consider something. Well, I went back and I looked at OSHA, and I'm here to tell you this is what OSHA says. It says if you're at my house, 4924 up to 5,900 feet, I need to multiply those approach boundaries by 1.08. So you're going to get a slightly bigger value as you go up in elevation. So if the restricted approach is 1 foot, if you're at my house, it might be 1 foot, 1 inch. All right, so there you go. Need to consider the altitude when you're looking at restricted approach. 130.5, arc flash risk assessment. Informational note about equipment doors was added, and the durability of the required arc flash signage is now addressed. All right, so 130.5b, likelihood and severity of estimates. When you're estimating the likelihood of an arc flash occurring and the severity of injury it could cause, then you need to consider the following items. And really, that's the name of the game, right? You need to do a shock risk assessment. You need to do an arc flash risk assessment. Both of those are determining the likelihood of something bad happening and how bad it would be if it did happen. Likelihood, severity. Number one, you need to consider the design of the equipment, including the overcurrent protective device and its clearing time. There is a big difference between these two fuses. All right, the fuse on the left is a current limiting fuse. The fuse on the right is not a current limiting fuse. The current limiting fuse is going to result in a much lower incident energy, right? With everything else being equal, right? The fuse on the left is going to have a faster operating time, which is going to decrease the severity. Is that going to decrease the likelihood? Probably not, but it's going to decrease the severity of something bad happening. So we need to consider the design of the equipment and the overcurrent device and its clearing time. We need to evaluate the condition of maintenance and operating condition of the equipment. Looking at this equipment, it appears to be fairly old, but it also appears to be well maintained. This looks like this looks like a normal operating condition where I could have normal operation of equipment. But if I was going to be, if I was in a scenario where I had to troubleshoot it and I have to work on it while it's energized, right? And I'm not in an electrically safe work condition, then I need to look at the condition of maintenance and operating condition of the equipment to figure out exactly where it can go wrong, how bad it would be. There you have it. We added an informational note that says, closed equipment doors do not typically provide enough protection to remove the need for PPE. Okay, closed equipment doors could certainly remove the risk of electric shock, right? If I can't touch the bare conductor or bare component, well then, yeah, there is no shock risk. Does that remove the risk of arc flash? Not necessarily. If I have an arc flash, the pressure wave, the arc blast, I should say, could knock the cover right off the equipment, right? Especially if I have like a hinged door. It can blow the hinges off. So closed equipment doors do not normally provide enough protection to remove the need for PPE. And this is just an informational note reminding us of that fact. 130.5H, equipment labels. Unless located in dwelling units, switchboards, panel boards, industrial control panels, meter socket enclosures, motor control centers, and similar that are likely to require examination, adjustment, servicing, or maintenance while energized must be field marked with a label containing the following information. All right, so what does the label have to say? Number one, always got to tell me the voltage. All right, so here it says 208 volts. Know the voltage. Number two, always have to have the arc flash boundary. Always. So this tells me that the arc flash boundary is what? 47 inches, which means I need arc flash PPE if I'm within 47 inches of the arc flash source. Item 3, I can have one or more of these. Option A, I can have the available incident energy and the corresponding working distance. Okay, which means you went through and you did the calculation. Okay, so item A, the incident energy and corresponding working distance, or the arc flash PPE category in table 130.7 C15A or B for the equipment, but not both. You're going to do one or the other. You're either going to do the calculation method or you're going to do the table method. All right. If you do the calculation, tell me the incident energy. If you do the table method, then you're going to tell me the arc flash PPE category, category 1, category 2, etc. Or you could just tell me the minimum arc rating of clothing. All right, so you go back, tell me the voltage, tell me the arc flash boundary, and tell me the arc rating of clothing, right? So you know the boundary, 47 inches. If you just tell me, hey, wear 35 calorie equipment. All right, I know what to do. I know my shock protection, right? So I know what category my gloves need to be, and I know how far away the arc flash boundary is, and I know what to wear. So tell me the incident energy, or the category method, or the minimum arc rating of clothing. Or option C. Listen, this is just Ryan Jackson talking, okay? Not 70E. You're insane if you use site-specific level of PPE, okay? Site-specific level of PPE, which could mean like, oh, category orange. What does that mean, right? If you say, hey, use PPE level brown or level 7, what does that mean? Maybe that means something to the people that work there. Maybe, probably not. Does it mean anything to like an outside contractor? What if something happened and a person got injured and the attorney or the expert looks at it and says, what the hell does site level specific category brown mean? Why didn't you just say category 3, or why didn't you say 10 calorie or whatever? You had to be cute and make this site specific level, and now we have a dead body, right? So don't try to do a site specific thing. Just look, tell me how to dress, all right? And let's not make it archaic, and let's not make it esoteric, so I don't have to have some sort of manual to tell me what it means, okay? Just tell me how to dress. We've got an exception that says, unless changes in the system make the label inaccurate, labels applied before the effective date of this edition of 70E are acceptable if they complied with the requirements for labeling when they were applied. Okay. Do I need to go through every 3 years when they make a standard and put new labels on? No, we don't, unless we've changed the system to make the labels inaccurate. The calculations and the data must be documented and reviewed for accuracy at 5-year maximum intervals, and the label has to be updated if changes have made it inaccurate. All right, so review it every 5 years, and if you don't need to update it, then don't update it. But if you do need to update it, well, then you need to update it. New to this version of the code, the label must be suitable for the environment in which it is installed. Yeah, makes sense. I mean, it didn't say this before, so it probably should have, and now it does. But yeah, let's not write it with a Sharpie or something. The label must be suitable for the environment in which it's installed. Lastly, the owner of the equipment is responsible for the documentation, installation, and maintenance of the field-marked label. All right, so who puts the label on? Well, it's up to the owner of the equipment to make sure that the equipment is labeled. In the National Electrical Code, we cover the installation in the NEC. In the NEC, it just says, hey, put on a sticker that says warning arc flash. In the standard for the workplace, it says whoever owns the equipment, right? Whoever owns the workplace, they have to make sure it has a label that has all of that material on it. The voltage, the arc flash boundary, and one of the options that tell me how to dress. 130.7, personal and other protective equipment. The rules for gloves were clarified. Okay, so rubber insulating gloves with protectors are required if there's a danger of hand injury from electric shock. Gloves have to be rated for the appropriate voltage. All right, so here in the picture, you've got your gloves, your rubber insulating gloves, and you've got your protector over it. And hand and arm protection is required if there's possible exposure to arc flash burn. Heavy-duty leather or arc-rated gloves and arc-rated clothing complies. All right, so here in the picture, I'm showing 3 gloves. Now listen, I'm not going to tell you what to do, but I am going to tell you this. If you just wear the rubber insulating glove right over your hand for a substantial length of time, you're going to start feeling nasty. You're going to start sweating, and it's going to be gross, all right? And here's the thing. If it gets too nasty and gross, people just don't want to do it. One thing that you can do really easily, and this is for a couple of bucks, and look, I don't know your financial situation, so I don't want to spend your money, but get yourself some glove liners, and you'll never look back, all right? So fire-resistant glove liners, and this is just for comfort. All right, but now I've got these glove liners on underneath the gloves, and now I can wear these things all day long, and it doesn't bother me a bit. So, God, if 2 gloves isn't enough, Ryan, you got to wear 3? No, I didn't say you have to wear 3. I think your life's going to be better if you wear 3, all right? This is going to make it a lot more comfortable. Then, put on your rubber insulating gloves. Then, put on your leather protectors over them. Now look, 3 pairs of gloves, it is a little bit cumbersome, but you can see I can still move around with this stuff. It's not like I'm wearing, plate mail armor. So make sure you got your gloves. Make sure you got your make sure you have your protectors over them. I almost said leather protectors. Top of the cuff of the protector must be shorter than the insulating glove by the value shown in table 130.7 C7A, and the voltage ratings must be adhered to. What it used to say is the length of the gauntlet. Okay, what does that mean? Well, I don't know what a gauntlet is, right? I'm a dumb electrician. What's a gauntlet? Distance from the protector to the glove, all right? Has to be not less than the value shown in the table. And you can see it's 1 inch. Well, it's 1/2 inch for category double aught and 0 gloves, and that'll give you up to 1,000 volts, all right, so 1/2 inch. Once you get a little bit higher than that, it's 1 inches, and it gets bigger the higher the voltage you get, which is pretty predictable. All right, 130.8, other precautions for personnel activities. Item M, reclosing circuits. No longer talks about repetitive reclosing, because how many times is that? Makes sense. So what it said before is if a circuit breaker actuates, right, an overcurrent device opens automatically, then don't repetitively reclose it. Okay, well, what does repetitive reclosing mean? Is that once, or is that 100 times, or is it twice? And now it's actually more clear. It says if an overcurrent protective device opens a circuit automatically, then a qualified person must determine why it happened and if it can be re-energized safely. All right. Never underestimate the abilities of humans, right? I mean, I have no idea how this happened. I can just tell you that it did. This is at a facility where I teach every year, and they show me this series of pictures where somehow this car ended up smacking into this transformer and blew the transformer into smithereens. Did a circuit breaker or a fuse open when that happened? Absolutely. Would it be prudent to just walk up to that and say, wonder why that breaker tripped? Let's keep on figuring it out until, right? No. If the breaker tripped, we need to figure out why before we start resetting it. So manually reclosing a circuit breaker or energizing through a replacement fuse is not allowed until the fault has been cleared. All right, so we need to figure out why the overcurrent device opened, and we need to remove the issue that caused it to open. Unless it was just an overload, right? I mean, okay, well, somebody plugged in 30 hair dryers in the bathroom. That's why it tripped. Okay, well then fine. We can turn it back on, unplug hair dryers and what have you. But if it's a ground fault or a short circuit, we need to figure out what happened before we start turning things back on. The last change to talk about is in the annex materials. Yes, there were a couple of things in chapters 2 and 3, but not that many. And I want to keep this relevant to the people that work in several different locations, not just for batteries or capacitors, right? So if your world is capacitors and batteries and things like that in chapters 2 and 3, yeah, there were a couple of changes. But aside from that, annexes, 0.2.4 added item 13 for high impedance protected test points for measuring voltage with doors closed as an additional safety by design measure. All right, so let me grab my sample here that my friends with Grace Technologies were nice enough to send me. This is something that can be installed on the front of a switchboard or switch gear, and you can see it's got the wires that connect onto the equipment, and this is basically a test point. So if you've got high incident energies especially, so if you're working at a facility where this equipment has 30 calories of incident energy or 50 or 100 calories of incident energy, yeah, even if you dress appropriately for it, I don't want to be in a piece of equipment like that, right? So what if I could test for the absence of voltage without opening the doors and getting my hands and my meter inside the equipment? What if I could use a test point like this? So you wire this thing, it's permanently installed, right? So you install this on the door, you wire it into the equipment, and then when you want to test to verify the presence or absence of voltage, You can open it up, stick your test leads in there, and it will tell you what's happening with the equipment. Very, very nice option for safety by design, right? And now that was added in Annex O. The other thing that happened is we added a new Annex S for help with analyzing the conditions of maintenance. Annex S doesn't have a whole lot of information. One of the things in there is it tells you to take a look at NFPA 70B, which is the standard for maintenance. So NFPA 70, the National Electrical Code, NFPA 70E for safety-related work practices, and NFPA 70B for maintenance. A lot of people view that as kind of the trifecta for electrical equipment, and I'm one of them. I agree with that. You should have all three of those documents, and you should understand them. How do you install it? How do you maintain it? How do you work on it safely? So Annex S kind of brings NFPA 70B into the mix. All right, that's it. Not that much to talk about when it comes to 70E in the 2024 edition. But again, maybe that's a good thing. Maybe we've got it, maybe we've got it kind of figured out. And we are, the fact of the matter is, we are seeing less electrical injuries out there. We are. The graphs and the injuries, they're heading in the right direction. So what we're doing has been working. So we're at a point now, perhaps, where we don't need to make massive wholesale changes. Let's just keep on keeping on. Let's be smart. Let's work safely. And let's hug the ones that you love when you get done with a hard day's work. All right, everybody. Thanks so much. I hope you got something out of this video, and we'll see you on the next one. Be sure to like, follow, subscribe, and ring the bell.